Hello everyone. This video is going to show you how to draw a polyatomic molecular orbital diagram. We're going to be using the example of beryllium hydride. So the first step is to use VSEPR to determine the shape of the molecule. So we know that beryllium has two outer electrons and we have two hydrogens which each donate one electron. We know that beryllium hydride has no overall charge, so we don't have to account for any. We divide by 2, and so we end up with 2 electron pairs in the molecule. Since we know that beryllium forms 2 sigma bonds, one per hydrogen, we know that the shape of beryllium hydride is linear. So next, we need to consider the number of molecular orbitals. The number of atomic orbitals in the basis set is equal to the number of molecular orbitals. So if we start by considering hydrogen, we know that we have 2 hydrogen atoms, so we have two 1s atomic orbitals present, each of which has an energy of minus 13.6 electron volts. Next, we consider beryllium. Beryllium has one 1s atomic orbital with an energy of minus 128 electron volts. It has one 2s orbital with an energy of minus 8.4 electron volts, and it has one set of 2p orbitals, and those are split up into 2px, 2py, and 2pz. And those each count as a separate atomic orbital. They each have an energy of minus 1 electron volt. Okay, so now we can work out the number of molecular orbitals. So 1, 2, 3, 4, 5, 6, 7. So we have 7 atomic orbitals, and therefore at the end we will have 7 molecular orbitals. We can use this as a check to check our final answers later on. Okay, now we have to check whether the atomic orbitals will overlap considering energetics. We have to remember that for overlap to occur, the maximum difference between the energy of 2 atomic orbitals cannot be above 10 to 15 electron volts. Okay, we know that the energy of the beryllium 1s orbital is too low to interact with any of the other atomic orbitals, and therefore it will form a non-bonding molecular orbital. The two hydrogen 1s orbitals are quite similar to the beryllium 2s and 2p orbitals, so they will theoretically be able to overlap. So now the next step is to draw each possibility out. We know the hydrogen 1s and beryllium 2s will overlap, as well as the hydrogen 1s and beryllium 2p atomic orbitals. First, let's consider LGO1. This is when the ligand group orbitals are in the same phase. In this case, the ligand group orbitals are the two hydrogen 1s orbitals. Because beryllium hydride is linear, our atomic orbitals will overlap linearly. So if we draw the two hydrogen 1s orbitals in the same phase, like this, We can start by considering our hydrogen 1s and beryllium 2s atomic orbitals. If everything is in the same phase, we know it'll form a bonding molecular orbital. This bonding molecular orbital will be denoted by a sigma because it has complete rotational symmetry, and a subscript 1, which indicates that it was formed when LGO1 was the case. Now we have to consider our antibonding molecular orbitals. All we have to do for this is change the phase of the beryllium 2s atomic orbital. This will form the antibonding molecular orbital, which will look like this. We denote this with a sigma star since it's antibonding, and the subscript 1 because it's from LGO1. We have already considered the hydrogen 1s with the beryllium 2s, but we still need to think about how the hydrogen 1s will interact with the 3 beryllium 2p atomic orbitals. Let's start by looking at 2pz with LGO1. If we draw a 2pz atomic orbital and two hydrogen 1s atomic orbitals, on one side, the atomic orbitals are in different phases, so there is destructive overlap. And on the other side, the atomic orbitals are in the same phase, so there is constructive overlap. The destructive and constructive overlaps cancel each other out, so there is no overall bonding between LGO1 and the beryllium 2pz atomic orbital. Instead, we know it must then overlap with LGO2, which is when the two hydrogen 1s atomic orbitals are in different phases. This will form a bonding molecular orbital because both sides overlap constructively due to being in the same phase. The bonding molecular orbital will be denoted by a sigma subscript 2 because the molecular orbital contains LgO2. For the corresponding antibonding molecular orbital, we swap the sides of the LgO2 around. On both the left and right sides of the forming molecular orbital, there is now destructive overlap because each side is out of phase. So this forms our antibonding molecular orbital, which we denote with a sigma star and subscript 2. Now we can look at the molecular orbitals that 2px and 2py form. Let's first draw out LGO1 and LGO2. Here we will draw the atomic orbital pointing upwards, but remember that in reality 2px and 2py are perpendicular to each other. For this example, that doesn't affect the answer, so we can draw it like this. So in LGO1 we have both constructive and destructive interactions as like and opposite phases overlap. the interactions cancel each other out, so there is no overall bonding. So this combination of atomic orbitals will not form a molecule. It is the same for LgO2. There is an equal amount of constructive and destructive interaction, so there is no overall bonding happening. Therefore, we can say that 2py and 2px will form two non-bonding molecular orbitals. It's now a good idea to check that we have ended up with the correct number of molecular orbitals, so we have redrawn them all here. We can count 1, 2, 3, 4, 5, 6, 7. So we have 7 molecular orbitals, which is what we expected at the start. We can now draw our MO diagram. So here we go. We're going to draw the molecular orbital diagram for beryllium hydride with the information that we have collected so far. We are combining beryllium and 2 hydrogen atoms to form beryllium hydride, so we write that at the bottom. The lowest energy atomic orbital is beryllium 1s, so we draw that at the bottom of our vertical energy scale. We know that it will form a non-bonding molecular orbital due to its energy, so we can draw that out. The beryllium also has a 2s atomic orbital, which we draw above the 1s along with the 3 2p orbitals. We draw those directly above each other because they are degenerate. For the hydrogen atoms, they both have a 1s atomic orbital. Those are also drawn close together because they have the same energy. Now that we've set out the framework, we can start to represent the molecular orbitals. We know that the beryllium 2s and LgO1 form one bonding and one antibonding molecular orbital. The bonding molecular orbital is lower in energy than both atomic orbitals, and the antibonding molecular orbital is higher. We draw dotted lines between the molecular orbitals and the atomic orbitals they came from to show how they were formed. We can remember that the 2px and 2py form non-bonding molecular orbitals, so we can easily draw those out in the diagram. And finally, we have to represent the overlap between the beryllium 2pz and LgO2. They form one bonding and one antibonding orbital. The bonding molecular orbital is slightly higher in energy than the sigma-1 bonding molecular orbital, because the atomic orbitals that formed it are overall higher in energy. This molecular orbital comes from 2pz, which is higher in energy than the beryllium 2s atomic orbital that the other molecular orbital formed from. You don't have to draw out the molecular orbitals on the diagram, but it can be useful to keep track of what is left to include. You should, however, label your molecular orbitals with their names, so that's sigma and sigma star, or pi later on. We still have to draw our antibonding molecular orbital, which we do above the previous antibonding molecular orbital. Now that we have drawn the outline of our molecular orbital diagram, we can place the electrons in. The beryllium 1s and 2s atomic orbitals are completely filled, and its 2p orbitals are empty, although they still take part in forming the molecular orbitals. Also, each hydrogen 1s atomic orbital contains one electron. In total, we can see we have 6 electrons in the atomic orbitals, so we can put them into molecular orbitals starting from the lowest energy upwards. 1, 2, 3, 4, 5, 6. Now we can calculate the bond order, but we have to remember that non-bonding molecular orbitals are not included in the calculation. The bond order is the number of electrons involved in bonding MOs, so here that is 4, minus the number of electrons in antibonding molecular orbitals, in this case 0. Then we divide it by 2. This gives us a bond order of 2, and we know this is correct because beryllium hydride contains 2 sigma bonds, one from beryllium to each hydrogen. Now we are finished, and this is how to draw a polyatomic molecular orbital diagram.